Welcome. In this explainer, we're going to dive into one of the most fascinating ideas in modern AI, generative adversarial networks, or GANs for short. We're going to explore how we can teach computers not just to see the world, but to create within it, to make images, text, and sounds that are almost impossible to tell from the real thing.
Just take a look at these handwritten numbers. I mean, they look totally normal, right? Like something you'd scribble in a notebook. But here's the thing. No human ever wrote these. A computer, an AI, generated every single one. That's the power of a GAN, and today we're going to pull back the curtain and see exactly how this digital magic trick really works.
So before we get into any of the complicated code or math, the whole idea behind GANs can be boiled down to a really simple, really powerful analogy. Just imagine a high-stakes game between two players, a brilliant art forger and a world-class detective. Their constant competition, well, that's the key to everything.
Okay, so here's our roadmap. We'll start with that forager and detective story to really build up our intuition. Then we'll peek inside the machine to meet the two neural networks. After that, we'll get into the actual math, the rules of their game. We'll see how a major upgrade called WGAN fixed a huge problem. And finally, we'll uncover the one last rule that makes this whole thing work so well.
All right, let's start by formally meeting our two main characters in this digital cat-and-mouse game. It's their constant battle, their rivalry, that actually builds one of the most creative tools in AI today.
So what exactly is a GAN?
Let's map our story directly onto the tech. The forger is called the generator. Its one and only mission is to create fakes, fake images, fake text that are so good they can fool the other network. And the detective? That's the discriminator. Its job is to look at any piece of data it's giving and make a call. Is this real or is it a fake? Okay, so we've got our forager and our detective. But what does that actually look like inside the computer? How do they talk to each other? Let's take a look at the system's architecture. This diagram really gives us a bird's eye view of the whole setup. Let's just follow the flow for a second. It all starts on the bottom left with some random noise, which comes from something called the latent space. Think of it as a random seed of numbers. The generator takes that noise and, like a sculptor, transforms it into fake data. Meanwhile, up top, the discriminator gets fed two streams of information: real data from a training set and that brand new fake data from the generator. And its job is to tell which is which. You know, what's really clever about the generator is that it never actually gets to see the real images. It just starts with a random string of numbers, its own little block of digital marble, you could say. From that totally random starting point, its neural network learns to sculpt and shape that noise until it turns into a convincing but completely fake image. The discriminator, on the other hand, is our judge. It sees a mix of both the real deal from our dataset and the fakes coming fresh from the generator's workshop. And for every single one, it has to make a decision, outputting a probability of whether it thinks the image is authentic or just a clever forgery. So we get the players and the flow of information. But how do we actually make them compete? I mean, how do you get better at forging in a language a computer can actually run? Well, the answer is in the math, specifically in something we call an objective function. The trick is to create a single mathematical equation that perfectly captures this rivalry. We need one formula where the two players have opposite goals. The detective wants to make its score as high as possible by spotting fakes. The forger wants to make that exact same score as low as possible by fooling the detective. This setup is called a Minimax game. One player minimizes, the other maximizes. It's a perfect mathematical tug of war. And here it is, the formal rules of the game. Now, I know this equation looks pretty intimidating, but let's just walk through together. D is our discriminator, and G is the generator. The discriminator, D, wants to make this whole value as big as possible. It wants to maximize it. Look at the first part, log D of x. X is a real image. D of x is the discriminator's guess that it's real. If D is good, this is close to 1, and the log is big. Now the second part, log 1 minus D of G of z. G of z is a fake image. The discriminator wants to correctly say it's fake, so it wants D of G of z to be close to 0. That makes 1 minus that value close to 1, and again, the log is big. So D wins by making both parts big. Now, what about the generator, G? It only cares about the second part, and its goal is to minimize the whole expression.
The only way it can do that is by making d of g of z as close to 1 as possible, by fooling the discriminator. It's a beautiful mathematical struggle. So the training process is this kind of back and forth dance. In step 1, we freeze the generator. Tell it to just sit still for a minute, and we train the discriminator. We feed it real and fake images, and it adjusts its internal settings to get better at telling them apart. That's called gradient ascent, because it's trying to climb to a higher score. Then, in step 2, we flip it. We freeze the now smarter discriminator and train the generator. It makes a fake, gets a score from the discriminator, and uses that feedback to learn how to do better next time. That's gradient descent, because it's trying to push the discriminator score down. And we just repeat this over and over. Now, this original game was absolutely groundbreaking, but it had a really big flaw. Sometimes the detective would get way too good way too quickly. It could spot any fake instantly. And when that happens, the forger gets no useful feedback on how to improve and basically just gives up. The whole training process just falls apart. This graph shows the problem perfectly. The vertical axis is the feedback signal for the generator. The horizontal axis is how confident the discriminator is that an image is fake. Now, look all the way to the left where the discriminator is super confident the image is a fake. See how the blue and red curves get almost completely flat? A flat line means the gradient, the signal telling the generator what it did wrong, is basically 0. The feedback has vanished. The generator is flying completely blind with no idea how to get better. The solution came with a clever update to the game called the Wasserstein GAN, or WGAN. The biggest change is that our detective gets a promotion. It's no longer a discriminator, it's a critic. Instead of just giving a black and white real or fake verdict, a probability between 0 and 1, the critic gives a realness score, which can be any number. A really high score means, wow, that looks super real, and a really low score means that is obviously fake. And this slide just illustrates that change perfectly. On the left, you have the standard GAN. The discriminator just acts like a sorter, putting images into one of 2 bins, real or fake. It's a simple classification. But on the right, the WGN critic provides this continuous sliding scale of realness. That richer feedback doesn't just disappear and flatten out to 0. It means the generator always gets a useful signal telling it how to improve, even if its early fakes are absolutely terrible. And this leads to much, much more stable training. Okay, this new game with the critic is a huge improvement, but it needs one more rule to stop the critic from just giving out wild, chaotic scores. We have to put some limits on it to make sure the feedback it gives is always smooth and makes sense. So let's unpack this final critical piece of the puzzle. And that final rule is something called the one-Lipschitz constraint. I know it's a mouthful, but think of it as a rule for fair judging. It just means that if the generator makes 2 fakes that are almost identical, the critic has to give them almost identical scores. It can't give one a score of -100 and the other a +500. This constraint keeps the critic's feedback smooth and predictable, which prevents the whole learning process from exploding with crazy, chaotic signals. Now, the very first attempt to enforce this rule was a pretty clumsy hack called weight clipping. It just chopped off the network's internal values if they got too big. The original researchers literally called it a terrible way to do things because it often led to really bad results. The real breakthrough was a much smarter, more elegant solution called the gradient penalty. And this is it, the state-of-the-art formula that brings everything together. The first part is the WGN objective we just talked about. But the big innovation is that new term on the right, the gradient penalty. What this term does is pretty genius. It basically looks at the slope of the critic's scores, and if that slope gets too steep, if it's not a nice, smooth one, it adds a penalty. It gently nudges the critic to follow our Lipschitz rule everywhere, making the entire training process stable and incredibly effective. This final algorithm, this is the recipe that puts all those pieces together. It shows the whole training loop for a WGAN with a gradient penalty. You can see the steps right inside the loop. We train the critic for a few rounds, calculating its loss plus our new gradient penalty. Then we take a turn training the generator. This complete recipe is what powers so many of the most impressive and stable image generation models we see today. So there you have it. We've gone from a simple story about a forger and a detective, all the way to this incredibly sophisticated state-of-the-art algorithm. The ability for machines to generate new, convincing realities isn't science fiction anymore. And that leaves us with a really big question to think about. As this tech gets better and easier to use, how is it going to reshape our world? What does it all mean when the line between what's real and what's generated starts to fade away?